Thanks a lot. So, first of all, thank you very much to everybody at Waterloo who's put this together. I've really appreciated still having this connection to the rest of the Matroid community, even though I've been stuck in isolation, and I really enjoyed the talks over the last couple of weeks. So, yeah, thanks a lot. I'll be talking about quasi-graphic Matroids, and this is joint work with Daryl Funk and Daniel Slilati. And yeah, so carrying on with the trend from the previous talks, I'll be introducing each section with pictures of New Zealand. This is when I was camping in New Zealand. I woke up one day and opened the entrance to my tent and saw this fantastic view and was, I don't know, fell even more in love with the country. So yeah, we've seen a lot of beautiful parts of New Zealand, and maybe it would be good if we could get these talks sponsored by the New Zealand Tourist Board. In the first section, I want to talk not yet about quasi-graphic Matroids, but about frame and lifted graphic Matroids. These are two much better understood classes of Matroids which have been around for a while, which quasi-graphic Matroids are somehow based on or sit in between. Yeah, so I thought it would be good to get to know these two classes first. First of all, we'll spend quite a while on the frame Matroids, and then just a much shorter time looking at the lifted graphic Matroids. And frame Matroids are a generalization of the game graphic Matroids, which Dylan was talking about last week. But I wanted to start with something even more concrete than that, just to get a sense of where these constructions come from. So hopefully something you all know that we can take as a starting point is that if you have a graphic Matroid, then you can represent that with a matrix where the rows of the matrix correspond to the vertices of your graph. And you have one column for each edge, and in that column, you put a 1 at one of the end vertices of that edge, a -1 at the other end vertex, and zeros everywhere else. And so something that we can notice about the matrices that we get in this way to represent graphic Matroids is that they're very sparse, in the sense that every column has at most 2 non-zero entries. And so if we want just to put a slight twist on graphic Matroids, we could try looking at matrices where we put still the restriction that each column has at most 2 non-zero entries, but now we no longer require those entries to be 1 and -1. Okay, just they can be any elements of the field that we're representing over. So let's change some of the entries in this matrix. Now you'll notice I've still kept it so that in each column I have at least one entry being -1. Well, you can always achieve that by just scaling the columns appropriately, and that won't change the Matroid that's represented. And then, so that we can somehow keep track maybe more easily in this graphic picture on the left, I'll just label the edges where I changed the column with the other entry in the column, right? So this 2 is a label on this edge, we have a 3 as a label on this edge, and a 1/2 as a label on this edge. And to be concrete about this, I've had to label which direction I'm labeling this edge in, because, okay, this is a slightly technical point. If I'd rescaled this column so that instead I had a -1 in this entry, right? Then down here, I wouldn't have a 2 anymore, I'd have an entry of a 1/2, right? So that's saying somehow, if I think about this edge pointing in the other direction, the label shouldn't be 2, but a 1/2. So really what we've got here is labels on, as it were, the oriented edges of this graph. And if you want the label of an edge going in the opposite direction, you just take the multiplicative inverse of the edge in this direction.
Can
Okay.
I ask a question here?
Yeah, of course.
So I have a construction in my head that many years ago I tried to put this type of thing on it, structure on it. Is there a way to get this type of matroid if I have a directed graph? Is that something that generalizes nicely?
Okay, so if you, let me see. So if you have a labeled graph like this, then everything will be good. So if you start with just a directed graph.
Sorry, directed labeled.
Okay. But are you saying, I mean, is it directed labeled in the sense that the label of an edge pointing in the opposite direction should be the inverse of the?
Yes.
Yeah,
but
okay.
The thing that I'm noticing here is that you have certain edges that are not directed and certain edges that are. And I'm wondering if it generalizes further.
Oh, I'm sorry. Yes. No. That's my fault. That's because some of these edges, I still have a column which is 1 minus 1. So those edges, I could just put the label 1.
Okay, but I could also choose to to label it, or to throw an arrow on that edge.
Yeah, exactly. And since it's a 1, it doesn't matter. Wouldn't matter which way that arrow would be going. Right, because the multiplicative inverse of 1 is just 1.
Yeah. Okay.
Okay, so yeah, so sorry. So the unlabeled edges, you can think of them as pointing either direction and with the label 1. Okay, great. So I think that helped to clarify this a little bit. So thanks a lot for that. And now we have a matrix over here on the right, and we could ask ourselves, which matroid does it represent? It won't be the graphic matroid for this graph anymore. For example, this cycle won't give us a circuit anymore in the corresponding matroid because these two edges, I mean, the vectors corresponding to these two edges are no longer parallel, right? And if we look at this, this cycle here, and we try to find a linear combination of the corresponding vectors, which evaluates to 0, well, if we take this vector, if we want it to cancel here, we have to add on 2 times this vector. And then if we want that to cancel here, we have to add on 3 times 2 times this vector, so 6 times this vector. And then here we have a factor of 1/2, so we'd have to add on then 1/2 times 3 times 2, so just 3 times this vector, but then it doesn't cancel here, right? Okay, so the problem was that the reason why this cycle didn't end up giving us a circuit was that when we multiply these labels as we go around the cycle, we ended up with a value other than 1, right? If we consider a cycle where the product of the values is actually 1, then we do get a linear combination of these vectors equal to 0, namely this guy plus twice this guy plus twice this guy plus this guy. Okay, so let's call let's call cycles with this property, right? The property that when you go around the cycle, if you multiply all the labels together as you go around, that you get the value 1. Let's call those cycles balanced. Okay, and what we've seen so far is that the balanced cycles of this graph still give us circuits in the corresponding matroid, but the unbalanced cycles don't. So what other circuits are we going to get? Well, okay, so I mentioned that this is not a circuit, but we can at least take a linear combination of these two vectors, which is 0 at this vertex and non-zero over here. And similarly, there's a linear combination of these two vectors, which is 0 at this vertex and non-zero here. So by combining those two combinations suitably, we can get a linear combination of these 4 vectors, which is 0 everywhere. And this will give us a circuit in our matroid, which consists of the edge set of this union of 2 cycles, which just meet at a single point. Right, in a similar way, if we take now these 2 vectors, again, they have some linear combination, which is 0 here and non-zero here. So by combining that with the guy from these 2, which was 0 here and non-zero here, and interpolating suitably with this vector here, we can get a linear combination of these 5 vectors, which evaluates to 0. And so that gives us a circuit of the corresponding matroid, which consists of these 2 cycles together with a path between them. And you can carry on this analysis, and you can work out precisely what the circuits in a graph represented over such a matrix will look like. There'll be edge sets, first of all, of balanced cycles, and then of subdivisions of 3 more kinds of subgraphs. So first of all, we saw examples already of this tight handcuff. That's just 2 cycles which meet in a vertex. The loose handcuff, that consists of 2 cycles together with a path between them. And then the theta, which, if you take a subdivision of this guy, that just gives you 2 vertices and then 3 paths between them, which are disjoint except at those 2 vertices. So edge sets of each of those kinds of things in the graph will give you circuits. I suppose I should specify now, I'll never say this again, you can take this as read, but when I talk about thetas, tight handcuffs, and loose handcuffs, I always mean such that they don't already include a balanced cycle, right? Because if they did, then just that balanced cycle would already be a circuit. Okay, so if we take one of these frame matrices, then this gives us a complete specification of the circuits of the corresponding matroid. Now, something you might notice about this matroid is that the definition didn't actually make any use of the additive structure of the field, right? Where did we use the structure of the field at all? Only when we were defining what it means for a cycle to be balanced. And there we just said a cycle is balanced if when you take the product of the labels as you go around the cycle, that should equal 1. So that only uses the multiplicative structure. So you could ask yourself the question, what if we just try to do the same construction, but for any group, right? I mean, maybe not just the multiplicative group of the field, but an arbitrary group. Right, we can again define a balanced cycle to be one in which the product of the labels evaluates to 1 in the group. And we can just take the collection of edge sets that arise in this way and say, is it the set of circuits of a matroid? And the answer is yes. That is always the set of circuits of a matroid, and those are exactly the game graphic matroids, which Dylan was talking about last week. Okay, but sort of once you see that you can do this, you might start to get curious about sort of what exact properties of the collection of balanced cycles that you get in this way are you using in order to get that this construction gives you a matroid? Okay, or to make that question maybe more precise, let's say I have just some arbitrary set of cycles in a graph. Okay, and I'll just call those balanced cycles. And now I build some subsets of the edge set according to this recipe, and I wonder, when will this give me the set of circuits of a matroid? Okay, so there are some conditions which, or at least there's one condition which the balanced cycles will obviously have to satisfy. If I have some theta in the graph, and 2 of the cycles in the theta, let's say this one at the top and this one at the bottom, if those are both balanced cycles, right, then I can apply circuit elimination. I can eliminate some edge in this central path. And then looking at the shapes that are available, there's only one possibility for what the circuit could be that you get after elimination, namely it has to be this cycle around the outside. And so in particular, that cycle would have to be balanced. Okay, so if this is going to work, then in any theta, if 2 of the cycles of that theta are balanced, then the third one will also have to be balanced. And so I'll just call this the theta property, that you don't have any theta in the graph which has precisely 2 balanced cycles in it. And Zaslavsky showed that this is all that you need. As soon as that's satisfied, this construction will give you a matroid. So let's start making this a bit more formal. We can define a biased graph to consist just of a graph together with a set of balanced cycles, that's just any set of cycles in the graph which satisfy this theta condition. And now Zaslavsky showed that for any biased graph, if you run this construction, if you take the edge sets of subgraphs of these types, you will always get a matroid. And these matroids are then called the frame matroids for the corresponding biased graphs. Okay, and Zaslavsky also gave a really cute characterization of which matroids arise in this way. So this is nice. He showed that a matroid is a frame matroid of a biased graph in this sense, precisely when it's a restriction of some matroid which has a basis with the property that every element is spanned by a set of at most two elements of that basis. Okay? So this should be very reminiscent of the frame matrices that we started with, because this condition that in each column you have at most two non-zero entries, right? This is just saying that this column is spanned by two elements of the canonical basis for the free vector space on the set of vertices. And so although that basis is not present in the matroid, right? I mean, here we just said we take a restriction of such a matroid, so we can then delete the elements of that basis, we can get rid of those, and we'll get something which looks sort of like a matroidal generalization of this idea of having just at most two non-zero entries in each column. So this theorem of Zaslavsky somehow closes the circle and shows that this is the right matroidal analog of the things which are representable over these frame matrices. Okay, great. So I want to talk about also lifted graphic matroids. I'll say a bit less about those, but yeah, maybe I should jump back. Some of you, I guess, seeing this this notion of a biased graph and of a collection of balanced cycles, might have been reminded of Crépeau's theory of one-element extensions of matroids. So he was thinking about the following question. Suppose you have a matroid on a particular set E, and you want to build, or you want to understand all of the matroids on a ground set of size just one more, so with just one more element, such that when you contract that element, you get back to the matroid M. Okay? And he gave a really good characterization of these guys. So first of all, every circuit of M has to extend to a circuit of M dashed, right? Either it already is a circuit of M dashed, or it together with this new element E is a circuit of M dashed. And the first thing to notice is that just that information about which circuits extend by adding the new element and which ones were just already, which ones are still circuits in M dashed, this is enough to completely determine the new matroid M dashed. And so we just need to understand which collections of circuits can arise in this way, right? As the intersection of the set of circuits of the new matroid with those of the old. And he showed that, that the sets of circuits which can arise in this way are precisely those which are linear. I don't want to say today exactly what linear means. For our purposes, it'll be enough to know that for graphic matroids, at least, there's a very neat characterization of linear classes of circuits, namely this theta property, right? That no theta in G should contain precisely two circuits from your linear class. So what does that mean? That means that the one-element extensions of the matroid for a given graph G, they correspond exactly to the biased graph structures on G. Okay, so you might ask yourself, does this somehow give us back the frame matroids? Well, this is, okay, so first of all, this is giving us matroids on slightly larger ground sets. right, which have this new edge, little e. So, oh, yes. Oh, okay. Sorry, I might be hitting a microphone somehow. I'll try to stop doing that in the future. Okay, so, right. So, yeah, as I was saying, this extension is on a ground set which also has this element E. But if we want to get back a matroid on the same ground set, then we could delete this element rather than contracting it. Right? That'll give us back a matroid now on the same ground set. And you might think, is this going to give you back the same construction, these frame matroids? And the answer is, it almost does. It gives you something very, very similar, but oddly, just a little bit different. Namely, you have now as your circuits, you have the edge sets of subgraphs of the graph, which are subdivisions not of these 5 types of objects, but of these 5, where instead of the loose handcuff, we have just this bracelet, which consists of 2 disjoint cycles in the graph. Okay, but so you can see that these are 2 very similar, very closely related classes of matroid. And so we could ask ourselves, is there some natural class of matroids somehow bridging between these 2, some sort of intermediate construction of a class of matroids? And there are a few different approaches to this question. There are a few different ways that you might try to do this. And I want to look now at 3 of them with you. So the first goes right back to Zaslavsky. And he said, well, look, why don't we just say a matroid lies between the lifted graphic and the frame matroid for a biased graph if every independent set in the biased graph is also, sorry, in the lift matroid is also independent in the matroid, and every independent set of the matroid is independent also in the corresponding frame matroid. Okay, it seems like a straightforward idea. Then we have the quasi-graphic matroids introduced by Gielen, Gerards, and Whittle. And they had a particular purpose in introducing these quasi-graphic matroids. So they had noticed that the classes of lifted graphic matroids and of frame matroids are in some sense badly behaved. So Gielen, together with Rong Chen, had shown, first of all, that neither of these classes can be characterized by finitely many excluded minors. And secondly, that it's not possible to recognize in polynomial time whether a given matroid is, let's say, lifted graphic, if you have access to a rank oracle, let's say. Or the same is also true for frame matroids. You can't recognize them in polynomial time. So they hoped that by somehow building a class interpolating between these 2, they might get a nicer class, which does have these nicer properties. And and their approach was to take some properties that are possessed by both of these kinds of matroids and to just say, okay, we'll say a matroid is quasi-graphic if it has these nice properties. And which properties did they choose? Well, first they said that the rank of the edge set of any component should be at most the number of vertices in that component. And it's easy to see that that's true for lifted graphic and for frame matroids, because in any component, right, if I take just a basis of that component, then I can't have 2 different cycles in that, because otherwise I would already include one of the types of circuit, right? So that consists of maybe a spanning tree plus at most 1 more edge. Now, a spanning tree has number of vertices minus 1 edges, then we put 1 more back in, we have at most the number of vertices, many edges. Okay, and this second property is also fairly straightforward. So this says, if I take a vertex and I take an edge going from that vertex to the rest of the graph, then that's not spanned by the set of edges amongst the rest of the graph, right? And sort of that's combinatorially just easy to see if you look at these different kinds of circuits that can arise in the frame matroids or in the lifted graphic matroids, that none of them will be able to span an edge from a vertex to the rest of the graph using only edges in the rest of the graph, right? None of those, essentially this is saying none of those types of circuits has a leaf in it. And the way they phrased it was just to say that if you take the closure of the set of edges in the rest of the graph, then that includes, then that's included just in the set of edges of the rest of the graph and otherwise only contains loops. Maybe it contains a loop sitting at the vertex B or some loop sitting at the vertex B, but that's all you can get. And finally, a notion which I have dubbed sortographic. I think this idea goes back to Funk, to Darryl Funk. I'm not completely sure if he was the first one to come up with this, but I think so. And his idea was to go between these two. You just say, we know what types of circuits we should be getting, right? We have these pictures, so let's just impose that all the circuits are of the given types. So they should all be balanced cycles, or thetas, or tight handcuffs, or maybe some bracelets and maybe some loose handcuffs. Okay, and to be a bit more precise about this, for each bracelet, we can either decide, yes, we want that to be a circuit, then we'll call that a dependent bracelet, right? Or for some bracelets, we'll say, we don't want that to be a circuit, that'll be an independent bracelet, and then any way of completing that to a loose handcuff should give us a circuit. Right. And so, yeah, before I go any further with this, I want to point out that two of these approaches to building matroids between lifted graphic and frame matroids actually have a serious problem. Although I feel a bit bad saying that Zaslavsky's approach has a serious problem, because it's only a serious problem if your aim is to try to build a nice, well-behaved class of matroids. And that wasn't what Zaslavsky was doing when he introduced this notion. He was trying for something very different. But nevertheless, let's pretend he was and say that he runs into the following serious problem, which is that if we consider this particular biased graph, which just consists of a bunch of loops, in which every loop should be considered to be unbalanced, then what does it mean to say that a matroid sits between the lifted graphic and frame matroids in this case? First of all, every independent set of the lifted graphic matroid should be independent in this matroid. But which sets are independent in the lifted graphic matroid? As soon as you take two edges, that's already a bracelet, right? So the only independent sets are the sets of size at most 1. And then we also have the condition, every independent set of our matroid should be independent in the frame matroid. But actually every set is independent in the corresponding frame matroid, right? Because we just don't have any of the shapes that I was showing you earlier, right? Because these are not joined up, we don't get any handcuffs. So that's no restriction at all. So the only restriction we have on our matroid is that sets of size at most 1 should be independent. That just says it's a loopless matroid, right? And that's not a nice, interesting restriction. That's not giving us an interesting class of matroids at all. And the situation is even worse for these quasi-graphic matroids, because any matroid on this set, on the set of edges here, will be quasi-graphic. It's not too hard to check. In any component, you have that the rank is at most 1, because there's only one edge there, and so it's at most the number of vertices. And here we're allowed in the closure to put as many loops as we like, and everything is a loop. So these conditions are just vacuously satisfied. Okay, so how can we fix this up? Well, first of all, to fix up Zaslavsky's condition, we could say that the problem was that we had all these different components of the graph, right, which are somehow hanging around doing different things in the same component of the matroid and causing trouble in that way. So to prevent this, we might want to say that every component of the matroid is already included in a component of the graph. Okay? And this is not going to cause us any problems. So you might worry a little bit because in a lifted graphic matroid, it is possible to have a disconnected graph giving rise to a connected matroid. But by just sticking together the components at individual vertices, you can build a connected graph which represents exactly the same lifted graphic matroid. So we don't lose any matroids by imposing this restriction here. Okay. And then we have also the quasi-graphic matroids, and luckily Gielen, Heratz, and Whittle actually already noticed by the time that they got around to publishing their paper about this that there was a problem, and so they also introduced a further condition to fix this, namely that every circuit of the matroid should have at most 2 components. Okay, good. So now I want to get back to these sortographic matroids and say something about those. They have a slightly, I mean, a much smaller problem. Namely, we don't really know which bracelets or which collections of dependent bracelets we should take. Right? So I could phrase this another way. I could say, I take a biased graph, I take some set of bracelets in this graph, okay, any set of bracelets, and then I can just define a collection of subsets of the ground set according to this recipe, and I can see whether it gives me a matroid. If it gives me a matroid, I'll call that matroid sortographic, okay? But maybe it won't give me a matroid. So, so we have to be able to recognize when this is going to give us a matroidal construction. And I'll talk about that in the next section, where we'll also see that these last two approaches actually give you the same class of matroids. The top one gives you a slightly different class, and we'll come back to that later on. But Nathan, for now, yes.
Quick question about the previous slide.
Yeah.
The fix for Zaslavsky's thing,
yeah.
Does that preclude lifted graphic matroids? Because then if your matroid is just a dependent bracelet, then wouldn't that not satisfy this condition? Or sorry if you said this already.
Yeah, so what happens in that case is that there are some lifted graphic matroids which don't satisfy this. But in each case, you can replace the graph with one which is a bit more connected, where you just stick together those components of the graph, right, at single vertices.
Oh, okay. Oh, because you don't care about the matroids that you get out of this.
Right, and that will give you then the same matroid back from a bias graph which does satisfy this condition.
Gotcha, thank you.
Okay, yeah. Okay, so right, so I want to talk about now the quasi-graphic matroids, and the fact that these are the same as the sortographic matroids. This gives you somehow a good concrete handle on the quasi-graphic matroids. So this is the first theorem, that the quasi-graphic and sortographic matroids are actually the same. But we still have the problem that we have to understand which collections of bracelets we can make dependent and get a sortographic matroid in this way. Now you can give an account of when that happens somehow in terms of the bracelets, but it's not as concrete as we might like, and so I'd like to take a slight diversion and go around to a slightly different construction, which gives us these quasi-graphic matroids very concretely. And in order to get there, I'd like to consider whether it could be the case in this graph here, which just consists of these three loops and an edge joining these two, that, right, could it be that this bracelet consisting of these two loops is independent, so that we get this loose handcuff as a circuit, but that this bracelet here is independent? Okay, could that happen? And the answer is no, that can't happen, because if both of these were circuits, then we could apply circuit elimination, eliminating this edge and keeping this edge. And so after we do that, then we would have to get a circuit included in this set and containing this edge, right? And that's just not possible with the constructions that we had available to us. So the problem was that we wanted this cycle to appear both in some independent bracelet and some dependent bracelet. And it's possible to show. I mean, the proof in general is a little more complicated because these other two cycles could intersect each other in some horrible way. But it is possible to show in general that no cycle can be in both an independent bracelet and a dependent bracelet. Okay, each cycle has to decide whether it wants to appear in independent bracelets or in dependent bracelets. So in some sense, this is saying that we can partition up the cycles into two classes, right, which we'll call frame cycles, and the frame cycles want to appear in independent bracelets, and lift cycles, which want to appear in dependent bracelets. And now if you have a bracelet that consists of two frame cycles, then it should be independent, but when you form a loose handcuff from that, then you should get a circuit. If you have a bracelet that consists of two lift cycles, that should already be a circuit. And now we have the worry, what happens if we have a bracelet that consists of one frame cycle and one lift cycle? There, we just don't know what to say. I mean, that just shouldn't happen. And so we're just going to ban that. Okay, we're going to say there should be no bracelet which consists of a frame cycle and a lift cycle. Okay, or to put it another way, no frame cycle can be disjoint from any lift cycle. They all have to meet each other. Okay, so this gives us the notion of a proper tripartition of the set of cycles of a graph. So this is a tripartition such that we start with a biased graph. We start by setting aside some suitable collection of unbalanced cycles. And then we want to partition the remaining cycles into two classes, a class of lift and a class of frame cycles, such that every lift cycle meets every frame cycle. Okay, and that will be called a proper tripartition. And now if we have such a proper tripartition, we can try to build a matroid from it by taking as our circuits the edge sets of balanced cycles, of thetas, of these tight handcuffs, of bracelets where both cycles are lift cycles, and of loose handcuffs where both of the cycles in the handcuff are frame cycles. Okay, and we come back again to a question of the kind that we've seen a few times here. Suppose I take such a proper tripartition, right? And I build a set of subsets of the ground set just according to this recipe. When will that give me the set of circuits of a matroid, right? What conditions do we need on this proper tripartition? And the answer is we need no more conditions. This will always give us the set of circuits of a matroid. So for any proper tripartition, if you build the collection of circuits according to the recipe that I just showed you, that will give you a matroid. And what's more, the matroids that you get in this way are precisely the quasi-graphic matroids. Okay, so this gives you a very concrete way to build these quasi-graphic matroids, which is sort of nice for getting hands-on proofs of a lot of basic theorems about them. For example, right, there's a nice theorem that if a quasi-graphic matroid is representable, then it has to already be either a frame matroid or a lifted graphic matroid. And that's easy to show using Ingleton's condition applied to some pair of disjoint frame cycles and some pair of disjoint lift cycles. So I won't show you the calculation, but it's pretty straightforward. Okay, so once again, since this is one of the central things that I want you to take away from this talk, you can build quasi-graphic matroids according to this recipe. Okay, you just take some proper tripartition and you take the edge sets of these kinds of substructures. Okay. Now, you might also be asking yourself that, I mean, we had this condition, right? Every lift cycle should meet every frame cycle. That seems pretty restrictive. So are we going to get interesting examples? Are we going to get non-trivial examples with many, many cycles in both classes, but which still somehow always meet each other? And to answer that, I want to show you 3 different examples of ways that you might try to build such a thing. The first is a pretty small example. If we look at this graph, if we take these 2 cycles here to be lift cycles, and these 2 on the left and the right to be frame cycles, and we can assign the other cycles however we like to the 2 classes, because they all go through all the vertices, and so they all meet every cycle. Right, so if we divide them up like this, then we can see that every lift cycle meets every frame cycle, and so we're going to get a matroid on this graph, in which, for example, we have both this loose handcuff across here, and also this bracelet here. Okay, we could try to generalize that a little bit. We could take some complete bipartite graph. And on each side of that complete bipartite graph, we just stick in some cycle going through all the vertices of that side. Okay. And now these 2 cycles are disjoint, of course, but every other cycle in the graph has to meet both of them. So if I make these 2 cycles both be frame cycles and every other cycle be a lift cycle, then we have the property that every lift cycle meets every frame cycle. And so we will, again, get a non-trivial quasi-graphic matroid out of this graph. Or alternatively, we could take these 2 cycles here to be frame cycles rather than, to be lift cycles rather than frame cycles, and the ones in the middle to be lift. The ones in the middle to be frame. Okay. Yeah, there's a more interesting class of examples that I wanted to get to. And these are built on some sort of topological structure. So here, imagine we have a graph which is embedded into some surface. Let's say into the surface of a torus. Okay. And if you have a graph embedded in a surface, then there's a very nice collection of cycles that you can take as your balanced cycles that somehow capture this topological structure. You can just take those cycles in the graph which bound some disk in the surface. Okay? And now it's easy to see that these have the theta property. Let's say that we consider this guy which bounds some disk, and we stick another path down here such that this cycle still bounds some disk. Then pasting those 2 disks together, we get some disk which is bounded by this cycle. So this will still be balanced, right? Or if this path had gone through the inside, we'd have had some sub-disk of the original disk. In any case, it's straightforward to see that this gives you a biased graph. And now we have to partition up the unbalanced cycles somehow. And the unbalanced cycles all have non-trivial homotopy in this torus. So we could, for example, take all the cycles in this homotopy class, right, the ones which go around the torus this way, and we could make all of those guys be frame cycles. And we could take all the ones which go around the torus this way and make all of those be lift cycles. And this is already starting to look promising because those all have to meet each other, right? In fact, if we take two cycles in different homotopy classes, right? So two cycles in different non-trivial homotopy classes, then they have to meet each other. And so we just can decide for each homotopy class whether the cycles in that class will be frame cycles or whether they'll be lift cycles. And that will then always give us a proper tripartition of the set of cycles of our graph. And if we take some very fine mesh on the torus as our original starting graph, then there'll be a lot of different homotopy classes available. And so we'll have 2 to the power of that many, so an awful lot of different proper tripartitions of the graph, of the set of cycles of the graph arising in that way. Okay, so yeah, I wanted to take a little bit of time just at the end to go back to the other approach from Zaslavsky to these biased graphic matroids. So remember that a matroid was supposed to be biased graphic if all the independent sets of the lifted graphic matroid are independent in this matroid, and all of this matroid's independent sets are independent in the frame matroid. And we had to impose this extra condition: every component of the matroid is already included in a component of the graph. Now, you might worry that this condition here is not strong enough, that we could get some other kind of annoying examples. If we think about what's happening in this graph, it doesn't look great. This is a graph which consists of just 2 loops and then a path going between them. And so, right, so the first condition, that just says that any set which doesn't contain both loops should be independent in our matroid. Or to put it another way, in order to be dependent, a set has to contain both of the loops. And this condition, this is just saying the whole ground set should be dependent. Right. But we can satisfy those 2 conditions by taking the matroid which has just one circuit, namely this set of edges, or any set of edges that contains both of the loops, right? I mean, you can take whatever subset of the path you like. So this looks a bit ugly. But in fact, it turns out that these biased graphic matroids are nevertheless under very good control. And the reason is this theorem, that any biased graphic matroid on a 2-connected graph is necessarily quasi-graphic. In particular, any 3-connected biased graphic matroid is necessarily going to be quasi-graphic. And then you might have some less connected ones, but they could maybe be built up with some kind of 2 sums, you could hope. And let's actually look at that in more detail. So if you try to use some sort of construction with 2 sums to build some ugly looking biased graphic matroid, then, sorry, I wanted to prove that theorem, but I think I don't have time. Maybe I'll come back to that later on if I do, but I'd rather take the time to actually explain how you can build biased graphic matroids. Yes. So what might we try to do? We might try to take 2 graphs, each of which has a loop. Take quasi-graphic matroids on each of these 2 graphs, and then stick them together with a 2-sum, where we somehow eliminate these loops against each other. Right? If you think about what you can get with a 2-sum, if you're summing over things which are not loops, somehow you don't get anything new or interesting. And so you have to sum over these loops, and these loops should be, of course, unbalanced cycles. in the corresponding quasi-graphic matrix. Okay, but actually the presence of these loops turns out to be really restrictive. So we can check fairly quickly that if you have a quasi-graphic matroid on a biased graph with an unbalanced loop, then it has to be either a lifted graphic matroid or a frame matroid. Why is that? We have to decide for this loop which class it should go into. So let's say that this is a lift cycle. Okay. Now, the condition was that every frame cycle must meet every lift cycle. And they can only meet this cycle in this vertex. So every frame cycle has to go through this vertex. Okay, so we can't have two disjoint frame cycles, right? We can't have any bracelet of frame cycles. And that means if we just push all of the frame cycles into the class of lift cycles instead, we won't change the matroid. Right? We just call them all lift cycles. The matroid stays exactly the same. And that means the matroid is a lifted graphic matroid in that case. Okay, the whole thing is lifted graphic. And similarly, if this loop had been a frame loop, then the whole thing would have been a frame matroid. Now, if we stick together two lifted graphic matroids, we won't get anything. Well, we'll just get another lifted graphic matroid back. And similarly, if we stick together two frame matroids, we'll just get a frame matroid back. So if we want to get something interesting here, we should stick a lifted graphic matroid onto a frame matroid. And if we do that, and we look at what we get as the circuits, then we're going to end up with some weird circuits that look a bit like this. So they look a bit like I tried to get a loose handcuff, right? I took a cycle over here and a cycle over here, and I tried to join them up with a path, but then I just kind of gave up when I got to this cut vertex here and stopped the path at that point. So these kinds of things are called broken handcuffs. If you work a bit harder, you can actually get a complete characterization of which biased graphic matroids you're going to get in this kind of way. Right, so the construction you need is this. You start with a biased graph, and for each vertex of that biased graph, a further biased graph assigned to that vertex. Okay? And now what you do is, at each of these vertices, you hang a loop. And also, to each of these graphs around the outside, you add a loop. Then you take the frame matroid for this graph in the middle with all the loops, and you take the lifted graphic matroids for the matroids around the outside, and you just take the two sums, right, of the corresponding pairs of loops, so over the corresponding pairs of loops, and that will give you some matroid on this ground set. And now, if we think about what we will get as the circuits in this matroid, well, we'll get precisely the, so first of all, we'll get all the balanced cycles in any of these graphs. We'll get all the thetas. We'll get all the tight handcuffs in any of these graphs. We'll get all the loose handcuffs in the central graph and all the bracelets in any of the outer graphs. And then we'll get some extra stuff. We'll get two more types of circuit. Namely, we get some circuits that look like this. They consist of cycles in two of these outer graphs, together with a path joining the corresponding vertices in the inner graph. And then you have cycles that look like this. They consist of some cycle in the inner graph and a cycle in one of the outer graphs and a path joining the cycle in the inner graph to the corresponding vertex. Right? This could be a trivial path if that vertex already lies on this cycle. But this is essentially all that you get. And so these are called the broken handcuffs for this construction. And a matroid built in this way from such a collection of a biased graph and then a biased graph for each vertex, that's called a broken handcuff matroid. And now we get the following characterization. So this is slightly wrong. I realized too late there's a mistake here. This should say the connected biased graphic matrix. So The connected biased graphic matroids consist precisely of the connected quasi-graphic matroids and the connected broken handcuff matroids. So these are the only two possibilities, right? It could be given in this way from a proper tripartition, or in this way via the broken handcuff construction. Okay, I wanted to close with just a couple of open questions. So the first is not so open. This is just a question for Dylan, if Dylan is here. I was hoping he might be able to tell us, using some of the ideas from last week, whether the quasi-graphic matroids can be defined in monadic second-order logic. And then we can also ask whether the quasi-graphic matroids are nice in the sense that Gielen, Gerard, and Whittle were hoping. That is, can they be characterized by finitely many excluded minors? And is it possible to recognize in polynomial time, if you have a rank oracle, whether a matroid is quasi-graphic? And then finally, this last question somehow asks whether the constructions that I showed earlier are the only way to build quasi-graphic matroids. Sorry, to build even proper tripartitions. And this says, okay, suppose that I have some small n. Is there some large enough big N so that if I have enough lift cycles and enough frame cycles, I mean enough disjoint lift cycles and enough frame cycles, so there's no small set of vertices which covers all of the lift cycles or all the frame cycles, then I'm actually going to get something that looks like a part of a surface. I'm going to get a flat n by 2n wall in my graph, such that every cycle in there is already balanced. By that I mean, so around the edge of this wall, you have some separation, and I mean that every cycle sort of inside that, on the wall side of that separation, should then be balanced. And if anyone has any ideas about any of those questions, I would be very happy to hear from you, but I will stop and say thank you for listening.
Thank you, Nathan. Are there any questions?
I have a quick question.
Yep.
So you're known to think about infinite graphs as well. So is there a notion of biased graphs for infinite graphs that gives you interesting stuff like B-matroids?
Okay, yes, so yes, I'm trying to remember the details of this. So if I go back to the different kinds of circuits that were allowed in a biased graph, sorry, no, that were allowed in a frame matroid. Right. Okay, so first of all, so for, oh, no. Right, so first of all, for lifted graphic matroids, because all of these kinds of edge sets are finite, it's fairly straightforward to show that you get a corresponding finitary matroid if you have a suitable collection of cycles satisfying the theta property. And also, this collection of cycles will also give you a finitary matroid for any graph together with a collection of bias cycles satisfying the theta property. But you can allow a little bit more. You can get an infinitary matroid in which you allow as cycles, in addition to these types, double rays and sperm, where a sperm consists of a cycle with a ray coming out of it. Okay? And if you allow these as cycles, you still get an infinite matroid. And I think these matroids are a bit weird and are not super well understood. But yes, so you can do construction sort of along these lines, also in the infinitary world. I haven't thought about whether you can do something sort of quasi-graphic looking in that world. but possibly.
Thanks.
Are there any other questions?
Yep. It's not really a question. It's just a nice talk, Nathan. I enjoyed it very much.
Oh, thank you.
All of those questions are, the whole tour, New Zealand tourism thing's a bit on hold at the moment, I'm afraid.
Yeah.
I have no idea when anything's going to happen again. Yeah, those questions are all very interesting. You'd have to think the answer is yes for the MSO question, wouldn't you?
Yeah, I would think the answer would be yes for that one. For the others, I'm not so sure.
No, I think the others are super interesting but difficult, actually.
Yeah. But here I would expect that the answer would be yes, but I kind of would think that maybe the best strategy for finding that out is just to ask Dylan.
Yeah. Yeah, equally, yeah.
Any other questions? I have a question. Is there any kind of algebraic object which can represent some interesting subclass of the quasi-graphic matroids, just as groups, well, group-labeled graphs can represent subclasses of the lift and frame matroids?
No, not that I know of. No, as far as I know, these are just very far from being algebraically presentable. Which means it would be really interesting if you could have a characterization by finitely many excluded minors, right? Because these are somehow very far from representability. Right? So if you think about the examples that you get here, which are far from being lift or frame, they come from just making some sort of weird arbitrary choice on this torus, and right, of which homotopy classes you get. And so I just can't think of any way that you could algebraically code that up.
Okay. Are there any more questions? Oh, is that Dan? Dan, do you have your hand up?
Yeah, I was going to offer a bit of a response to what was said. I think Nathan really said what needed to be said, is that, you know, if you take any group that is neither the multiplicative group of a field nor the additive group of a field, and a gain graph over that group, in particular any quotient of the free group on two generators for the torus, you know, that gain graph is sort of an algebraic representation of these quasi-graphic matroids, but you can't tell which cycles are lift and which cycles are frame, as Nathan was saying.
Right, that makes sense. Are there any more questions? Well, if not, then thank you again, Nathan.